Hello, Miss Barber here. In this lesson titled Trigonometry of Right Triangles, we will explore ratios of the sides of certain right triangles and all right triangles in general, and also look at several applications. The objectives of this lesson are: 1. Be able to apply trigonometric ratios of a right triangle. 2. Be able to determine values of right triangles using special right triangles. 3. Be able to solve right triangles. And 4. Be able to solve trigonometric applications involving right triangles. Roman numeral 1. Trigonometric ratios. Consider the right triangle with theta as one of its acute angles. The side opposite the theta we call opposite. The side adjacent to the theta we call adjacent. And the hypotenuse of the right triangle we call hypotenuse. Complete the following trigonometric ratios. We define sine theta as the opposite side over the hypotenuse side, cosine theta as the measurement of the adjacent side over the measurement of the hypotenuse side, and tangent theta is the measurement of the opposite side divided by the measurement of the adjacent side. Sine, cosine, and tangent all have reciprocal identities. So for each of those, we use the reciprocal identity to get the ratio definition. Cosecant theta is hypotenuse over opposite. Secant theta is hypotenuse over adjacent. And cotangent theta is adjacent over opposite. Use whatever mnemonic device works for you so that you know these by heart. Roman numeral 2. Special triangles. We have two special right triangles from which we can easily calculate trigonometric ratios. In fact, from these two special right triangles, we are able to obtain the same standard trig values as we did from the unit circle definition of the trig functions. The first is the 45-45 90-degree right triangle. We obtain this triangle by drawing a diagonal that bisects a square of side length 1. In so doing, we bisect the right angle to get two 45-degree angles. Use one of the 45-degree angles as the theta of the right angle and apply the Pythagorean theorem, which states the length of the hypotenuse squared is equal to one of the sides square added to the other side squared. Then we would get that hypotenuse is equal to the square root of the sum of each side squared. We only take the positive root as distance has to be positive, and so we'll substitute in the values and get that the hypotenuse is equal to the square root of one side, which is length 1 squared, plus another side, which is also length 1 squared. Solving, we get that the hypotenuse is the square root of 2. Now let's check the ratio against a unit circle trig function of value theta equal to pi over 4 with the one in the unit circle. The sine of pi over 4 is also the sine of 45 degrees. With the unit circle, the sine of 45 degrees, or the sine of pi over 4, is defined as 1 over the square root of 2, with the denominator rationalized the square root of 2 over 2. And now with the ratio, the sine of theta, which is defined as opposite over hypotenuse. And with this special triangle, the opposite is length 1 over the hypotenuse, which we just computed as the square root of 2. See, we got the same values. We call this the 45-45 90-degree triangle. For the other special triangle, we consider the equilateral triangle with sides of length 2. Because it is equilateral, the triangle is also equiangular, meaning all three interior angles are 60 degrees. By the way, I could have chosen any length for the sides, but chose 2 to simplify computation. I labeled this triangle as triangle ABC and drew a perpendicular bisector from point A to point D, which bisects the segment BC. Then the length of CD, or dB is 1, and the angle CAD as well as angle BAD is 30 degrees. We split the 60 degrees. Now let's consider a triangle DAC. Angle CDA is 90 degrees, angle ACD is 60 degrees, and angle DAC is 30 degrees. The length of side AC is 2, that's how we drew it. The segment CD is 1 because of the bisector. And now I apply the Pythagorean theorem for this triangle to solve for the length of the perpendicular bisector segment AD. We are solving for one of the sides in the Pythagorean theorem. So, AD is equal to the square root of the hypotenuse squared minus the length of the segment CD squared. Then AD is equal to the square root of the hypotenuse is 2, so 2 squared minus the CD is 1, so 1 squared. Solving for that, we get 4 minus 1, or the square root of 3. Let's check the trig ratio of 30 degrees of this triangle against a unit circle trig function of theta equal to pi over 6. With the unit circle, the sine of pi over 6, which is also the sine of 30 degrees, is defined as 1 over 2, or 1/2. Now with the ratio, the sine of theta is opposite over hypotenuse, and with this special triangle, the sine of 30 degrees is 1 over 2. We call this the 30, 60, 90 degree triangle. Roman numeral 3, applications of trigonometry of right triangles. A triangle has 6 parts, 3 angles, and 3 sides. To solve a triangle means to determine all of its parts from the information known about the triangle. That is, to determine the lengths of all 3 sides and the measures of all 3 angles. Solve for A. Presented as a right triangle with 60 degrees marked on one side, the letter A adjacent to the 60 degrees, and the hypotenuse denoted as length 28. To solve this triangle problem, we're going to use a trigonometric ratio, and I'll start with that the cosine of alpha is equal to the length of the adjacent divided by the length of the hypotenuse. Continuing, we'll put in values. We'll say that cosine of, and in this triangle, the alpha is 60 degrees, and the adjacent is the letter A, the length we're looking for, and the hypotenuse is 28. We know that cosine of 60 degrees is 1/2, and that's equal to A over 28. Solving for the length A, 28 times 1/2 equals A, so we find out that the length of A is 14 units. Terminology. If an observer is looking at an object, then the line from the eye of the observer to the object is called the line of sight. If the object being observed is above the horizontal, then the angle between the line of sight and the horizontal is called the angle of elevation. If the object is below the horizontal, then the angle between the line of sight and the horizontal is called the angle of depression. If the line of sight follows a physical object such as an inclined plane or hillside, we use the term angle of inclination. A woman standing on a hill sees a flagpole that she knows is 60 feet tall. The angle of depression to the bottom of the pole is 14 degrees, and the angle of elevation to the top of the pole is 18 degrees. Find her distance x from the pole. Let's get a sketch of this. So I'll let this dot be her line of sight, and she's on a hill, so we have a flagpole that is known to be 60 feet tall. Her angle of depression to the bottom of the flagpole from the horizontal is 14 degrees, and the angle of elevation from her line of sight is 18 degrees, and we want the length x. That's the distance from her line of sight to the flagpole. Now, If we know that the flagpole is 60 feet in height, then we'll let one part of the flagpole just be the distance y, and the other portion would be 60 minus y. So let's use some trig identities. We know then that the tangent of 14 degrees, which is going to be opposite over adjacent, will be 60 minus y over x, and the tangent of 18 degrees, also opposite over adjacent, will be y over x. Let's isolate the y in both of the equations. For the first one, let's multiply through by x, so you get x times the tangent of 14 degrees is equal to 60 minus y, and solving for y, we get y is equal to 60 minus x times the tangent of 14 degrees. For the second equation, solving for y, we'll get y equals x times the tangent of 18 degrees. Now let's set the y's equal to each other. Then you'll get 60 minus x times the tangent of 14 degrees is equal to x times the tangent of 18 degrees. We need to solve for x. So I'm going to put everything with x's on one side. That is, I'll get 60 is equal to x times the tangent of 18 degrees. And then add the other term, which would give us plus x times the tangent of 14 degrees. Continuing to solve. If you factor out the x, we will end up with, let's see, 60 equals x times the tangent of 18 degrees plus the tangent of 14 degrees, and the exact solution will be 60 divided by the quantity tangent of 18 degrees plus the tangent of 14 degrees equals x. We are looking at the face of a TI-84. When working with trig, always check the mode. So push the mode button. Make sure that it is in degree form. We're good with that. Now let's compute. We will do 60 divided by the quantity, so select parenthesis, tangent of 18, close the parenthesis, plus the tangent of 14, close the parenthesis for the tangent and for the expression in the denominator. Press enter, and we get that the distance is 104.4845284, round it to 104.5 feet. That is, we'll say that the answer is roughly 104.5 feet.